Starting it now.
Hello, Professor. So today we're gonna talk about our second presentation of plastic analysis of beam. So our group consists of Abdullah Lanzi, Charles Bermo, and myself, Subriani Ruzani. So the first problem is asking to determine the plastic collapse load F using the hinge-by-hinge analysis method. So the structure has a uniform load of 0.01 F kips per inch, 1.9 F kips, and 1.3 F kips, plus the vertical reaction forces applied at points A, C, E, and G. And also there is a moment at point A. So here we have. Can you go back? So here we have like the procedures that we use to solve this kind of problem using also Mustang program modeling. So the first step is saying that an analytic analysis is performed on the original structure subjected to the given set of loads. These loads have a relative magnitude in proportion to those at the collapse condition. This set of loads is referred to as the reference load. The second one is the load factor at each point is computed by dividing the plastic moment capacity by the moment at the point due to the reference load. The location of the smallest load factor on the beam is the location of the first plastic hinge or hinges. The magnitude of the smallest load factor is the controlling delta F. And our reference load in this problem was F equals 1. So step number 3 is talks about the displacement and internal moment at all points of the original structure subjected to the set of loads obtained by multiplying the lowest load factor with the reference load as computed by scaling up the result of the analysis of the original structure by delta F. Number 4 is the remaining moment capacity at each point is computed by subtracting the moment at each point from the plastic moment capacity. Number 5 is the original structure now modified by inserting an internal hinge at the location of the first plastic hinge. For number 6, an analytic analysis is again performed on this modified structure using the reference load. For number 7, the load factor at each point is again calculated by dividing the remaining moment capacity at each point by the moment due to the reference load applied on the modified structure. The second plastic hinge or hinges is at the location of the smallest load factor, and the magnitude of the smallest load factor is the controlling delta F. Number 8 is the displacement, and the internal moment is scaled again by delta F. So after we insert our initial model using F equals 1, the moment diagram is shown in the slide here, and the maximum moment was found as minus 89.19. So this slide shows that the first hinge was added at point A, and the result of the running the moment diagram was found that the maximum moment is minus 91.94. And the second hinge was added at point C, and the moment diagram is as shown in the slide, with the maximum moment about Z of 121.7. The third hinge was added to at point E, and the result of the moment diagram is shown here, with a maximum moment about Z of 121.7. So the last hinge was added at point like G, and it shows that the structure collapse when adding the hinge at point G.
Good evening, Professor. The last hinge was added at point F. So this is a table of the data for problem 1. As you can see, the cumulative delta F is, of course, going to increase as you're adding the delta F from the following hinge onto the total before it. Moment A reached the plastic moment at the and was the point where the first hinge was created. Therefore, that one's going to represent MP all the way down. Then MC was the second point to reach plastic moment, then ME, and then lastly MF. And that's what you can see here. And then it became an unstable structure once the moment at F reached plastic moment. So here's a hand-drawn loaded moment diagram at the collapse condition for problem 1. This was just done by using the original problem we were given and multiplying the given loads by our cumulative F at the collapse condition. So this was 0.01 times 234, 1.9 times 234, and 1.3 times 234. And this is the resulting moment diagram, which could not be displayed in Mastan because it's an unstable structure, so it will not run the analysis. And there are hinges now located at point A, point C, point E, and point F. So for the second part of this problem, we were to use a first order inelastic analysis in Mastan 2 to determine the plastic collapse condition for the same beam that we had before. We used just F equals 1, so our initial beam was the same that we had originally built in Mastan to do part 1. Simple step solution type, increment size of 1, a maximum number of increments of 10,000, and maximum ratio of 1,000. And then we ran the inelastic analysis. And the results were very similar to the results in part 1. Mastan would not give me any more accuracy beyond 4 significant digits. So these are the results you see here: 162 at the first hinge, then 205, 221, and 234. And those are in kips. Here is the deflection diagram at the collapse condition by the first order inelastic analysis. And of course, these little yellow triangles or bow ties represent the hinge locations. So again, you see the 162 at point A, 205 at point C, 221 at point E, and 234.8 at point F. And this is the moment diagram at the collapse condition created by the first order inelastic analysis. And you can see at points, again, A, C, E, and F, the plastic moment of 14,500 has been reached. So problem 3 just asks to discuss the reasons for any differences in the two nonlinear analysis results, and the differences were extremely minimal. Just generally speaking, a first order elastic analysis uses loss of rigidity at one support at a time via the creation of hinges. And this is repeated until an unstable structure is achieved, which is what we did in part one of this problem. And then a first order inelastic analysis runs through load increments at a specified rate until overall plastic collapse is achieved, and it's recognized by a major change in the deflection. And in mass tan, it prompts you and asks if you want to continue past that point. For this particular problem, second order analyses were not required since it's just a simple beam and it is different than a more complicated structure like a building, in which case there would be more axial loads with the beam columns. So a second order analysis would be required for that scenario. And that about wraps up our presentation. Thank you very much for your time.